So we need to get into the diagram we're going to use for electron configuration, but we need to remember that these electrons don't move around in a circular orbit like we were thinking with the Bohr's model, but they do have distinct energy levels in between them, and each level holds certain sub-levels and orbitals in those. Each energy level is defined simply by how far it is from the nucleus, meaning the protons and neutrons of the atom. So your first one out would be N1, then N2, then N3, then N4, and according to the periodic table, we can go all the way up to N7. So higher level, further from nucleus, higher energy. With those sublevels, we have 4 different types of sublevel. We have an S level, a P level, a D level, and an F level. Each of those sublevels have different numbers of orbitals. So in the S level, it only has 1 orbital. In the P, it has 3 orbitals. The D, it has 5. And the F, it has 7. But each one of those can hold 2 electrons. So that means you can get a maximum number of 2 electrons in the S level. You can get 6 electrons in the P level. You can get 10 electrons in the D level and 14 electrons in the F level. Now, before we can start the actual diagram, we need to understand some different rules and principles, okay? So, a FUBA principle is basically you're going to fill the lowest energy level and sublevels first. That means 1s has to be filled up with electrons before 2s can start to be. And then 2s has to be filled up with electrons before you can start to put them into P. So this can be a little bit interesting when you look at how this is actually lined up on the periodic table. Notice these are actually labeled as 3, 4, 5, 6, even though they're on 4, 5, 6, and 7. And these are actually on 6 and 7, but they're labeled 4 and 5. But it's because you just follow it straight over to know what fills up first. So 1s, then 2s, 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, 4d, 5p, 6s, 4f, 5d, 6p. Yes, it can be a little bit confusing because of the difference in the numbers lining up, but as you can see on the periodic table, you can follow it quite smoothly to figure out where those electrons go. And then there's a trick when we're doing something without this that I'll show you in the next video. So let's look at 2 more rules, Hund's rule and the Pauli exclusion rule. So with Hund's rule, it basically states that you're adding 1 electron to each orbital before doubling up. So notice if I'm looking at nitrogen, it has 7 total electrons, and it has 3 different sublevels with the amount of orbitals in each. So our S's only have 1 orbital. So you can go ahead and put 1 and 2 in that 1s, and then 1 and 2 in the 2s. That uses 4, but we have 3 left. And the P sublevel has 3 different orbitals. You have to put 1 electron in each one before you can start to double up any of these. And since nitrogen only has 3 electrons left at this point, then you just add the 3 going up. Now, because of the Pauli exclusion principle, we get that the electron spin is going in different directions. So notice that when I do double up, 1 I point is up, 1 I point down, just to indicate that I have 1 electron in one spin and 1 in an opposite spin. And it doesn't double up until each orbital is filled. So this again provides the location of all electrons in the ground state. Remember, excited state is when it gets filled with energy and they jump orbitals. But this is the ground state, so nothing's excited. It's how it would be, and a lot of these are for the neutral atom, as you would know in the periodic table, meaning it has the same number of electrons as it does protons. So here's oxygen. Oxygen is element number 8, so it's going to have 8 electrons. And here you can see those Hund's rule and Pauli exclusion again. We fill up the 1s first, 1 and 2. Then 2s, 1 and 2 electrons going in opposite directions. But then with the 4 we have left, for each of the 3 orbitals in the P, 2p, you have to go 1, 2, 3. Now that they're all filled, then you can start doubling up. So let's make one of these electron diagrams, and we're going to need a periodic table. Let's do one that's slightly more complicated than the examples we've looked at before. Let's do, what do you say, let's do aluminum. So right here we have aluminum. In fact, I'm going to go ahead and mark that out so that we can see it. Here's our aluminum. Yay. Notice that it is on the third period, and its atomic number is 13. So that means we're going to use 13 electrons as well. And look at the orbitals it has to go through. This is 1s, 2s, 2p, 3s, 3p. So I'm just going to start to draw those diagrams out. I said I had 1s, and we know it has one block in it, right? Only one orbital. Next we had 2s, and it also only has one orbital in it. But then we had the 2p, and it has 3 different orbitals in it. Then we had a 3s, and it's just going to have the one orbital, and followed by the 3p. That's 5. And it has 3 orbitals in it. Now remember, I also said that it had 13 electrons. So all we're going to do is we're going to start to fill up these electrons in each of the lowest energy first. So that's our 1s. Let's put 1 electron. We still have another, so let's go ahead and put another one going in the opposite direction, thanks to the Pauli exclusion rule. Then, because of Hund's rule, we go to the next energy level. That's 2 goes in there, so that's 4 electrons total. And then for 2p, we start to add 1, 2, 3. And then, like I said, we have 13. We've only used 4, so we still have 9. So that's 1, 2, 3 more. We have enough to go down. 1, 2, 3. All right. So now we've used a grand total of 10 of our electrons. We have 3 left. So I can put 1 here, and I have to fill up that one because of Hund's rule. And then I only have 1 left, so I'm going to put 1 electron there. Now that I have this, I know that this is aluminum. And it's aluminum because we can see how it fills each electron level that aluminum would have. And that's how we would do the electron diagram. Now that we understand how it works with putting the electrons in all of these different orbitals and sublevels and things, we can start to look at the notation, which is what the entire next video is going to be on. And it ends up looking more like this, so it takes up a lot less space than the diagram does. And each of these will tell us the same basic thing. It tells us the energy level that it's on, the sublevel we're using, and the number of electrons in it. And so this allows us to designate what oxygen would be. Remember, we looked at the diagram of oxygen earlier. This is the exact same thing, but written in the notation. We'll learn that next time.